Good afternoon, Professor.
Hello, guys. Hope your long weekend was good. You relaxed and also had some options to study. Yeah, let's see. Some people are still joining us. Yeah, hello, everyone. Nice to see you again. Okay, so we continue working with two-dimensional motion, and I guess maybe one more. Yes, sure. If you have any questions, you're welcome to ask on the way. We will try to address them. So I believe that one more lecture, like online class, will dedicate to one-dimensional motion, and also like afterwards we will switch to next topic, which is laws of motion. But today I would definitely like to address two more very general and important cases of projectile motion and also some complex motion when we have a superposition of motion along one axis and also rotational, like some uniform circular motion. So it's kind of a case of rolling a wheel, which is kind of very important and illustrative how different velocities should be added and how you calculate total velocity with respect of certain frame of coordinates. Okay, so there is a question, could we use J equal 9.81 in calculations? Yes, sure, this is the correct number. Usually it's 9.8, but if other parameters in the problem are given with more accuracy, like high accuracy, then you just go for 981. Usually you don't need higher accuracy for the acceleration of free falling. Yeah, hello guys who just joined us. And yeah, if you have any questions, you're welcome to ask. Okay. Is it okay to use 9.81 on long kappa? I think so. I'm not sure exactly, but it should be either 9.8 or 9.81. I will, yeah, I think that the best approach will be to contact our long kappa administrator, so he would possess more information on this question. But also check on the accuracy of parameters which are given in the homework. So do we have assessed homeworks on long kappa? I believe, yeah, you should already assessment on some homework problems, and like double check this because it's already week number 3, so you should be able to get your assignment and solve the problems, because this, from starting from week number 3, we will have all homework assignments graded. Yeah, this is a good question with in terms of problems on exams. I believe that these data analysis problems will not be included in midterms and exams. I just had a short discussion with other professors, and I guess there is an understanding that it would be better if we skip them and focus on physics. So definitely the main goal of our course is to help you to understand physics and physical concepts, not really do some too much of statistical analysis. Yeah, so that is, I believe, very reasonable. So we will try to skip these problems of data analysis. By the way, best to my knowledge, you should have already get some attached document with data and error analysis instructions attached to your first lab. If by any reason you don't have it yet, I, just in case for you, uploaded it to Moodle, so you can find these files there. So it has quite reasonable outlook of data analysis and like error analysis. That could also be helpful for you. But most of the problems will be focused on physics, and that's why we are trying to understand really physics behind all these theories and problems. So this is the main goal, and I believe that now I would like to discuss like with you 2 specific cases of 2-dimensional motion. So hopefully we have enough time for that. So probably let's start with this. I will switch. Oops. I will switch the camera. Yeah, so first case, the midterm exam, I have another question here. The midterm exam will be on Kappa, not on Moodle. We'll be also solving problems, but I guess closer to the midterm, you will get more information on it. Okay, so let's consider one of very important cases of 2-dimensional motion. This is projectile motion. So let's assume we have system of coordinates x and y. We have at the origin of the coordinates some body which at 0 time is thrown with the velocity v0 at some angle theta to the horizon, to the axis x, and it will follow this trajectory. It will go up and down. And what is interesting for understanding, let's start from 2 key points here. Let's say point 1 and point 2. So point 1, it's a maximum, defines maximum height this body will reach. Yeah, so here is the height. And also point 2 with respect to the origin of the coordinate will define like L, it's a distance this object will travel along axis X. So from our previous discussion, we clarified that position of and movement of any object in 2-dimensional or multi-dimensional system of coordinates can be described by radius vector, which is some initial position plus initial velocity multiply the time, and plus acceleration, in case we consider like constant acceleration, multiply t squared divided by 2. So projectile motion is also a case of of two-dimensional motion with constant acceleration. It's actually minus g because it's directed down in opposite direction from the y-axis, and that's why this approach is valid in this case. So let's first consider two components of velocity which we have, because this can be projected on axis x. It will be vx and vy. So we have vx equal to v naught multiply cosinus theta, and vy equal v naught multiply sinus theta. So we have components of velocities, and taking into account these components of velocities and our system of coordinate, in the initial position of our body is at 0 at the origin of system of coordinates, so y and x naught are 0. That's why we can write expressions for the change of coordinates along axis x and axis y. So let's start with axis x. So as I mentioned, x0, x naught, like initial position is 0 because it's in the origin of coordinates. Then we have v naught multiply cosinus theta multiply t, and this velocity is constant along the axis x. We don't have any friction with air, and there is no other reasons our velocity drops over time. So this is how coordinate x will change over time. Then let's check what is happening with coordinate y. So what do we have? We have initial position is also 0, so we skip that part. Then we have v naught multiply sinus theta multiply t, and minus gt squared divided by 2. So this is acceleration of free falling, and this definitely will have an impact on how our body will move along axis y. So let's say, starting from, oh, actually you didn't correct me, but I missed something here. So here v naught, y, like velocity along the axis y, will not be just v naught multiply sinus theta. It has to be v naught times sinus theta minus gt, because it changes over time since we have this acceleration, constant acceleration g. So this is the expression, and this is not constant over time. So starting from maybe question number 1, let's ask, what is the maximum height this body will go up along the axis y? So we can answer this question from this equation for the velocity vy. We know that at the highest point, this body will just stop. It will not move neither up nor down with respect to y-axis. That's the highest position. And in that case, we can say that vy will be equal to 0 at height h. And then we have 0 equal to v naught multiply sine theta and minus gt, I don't know, let's call it prime, some time at which it will reach the highest point. So from here we can define at which time this body will reach the highest point, and this will be t prime equal to v naught multiplied sinus theta divided by g. So this is the time, and now if we substitute this time in the y coordinate, we will get the answer to our question. What is the height? Because it will be y at time prime, t prime. So another approach, again, you can define the total time which this object will move in the air, while this projection motion will be going. I mean, yeah, we will. So there is a question: is it better to use this equation, which allows us to eliminate time? Yeah, you can go for this approach. There are many approaches to answer this question, so you just need to see possible ways, and please don't keep in mind all these final equations, because it's not really necessary. You need to understand initial conditions, and then based on the system of equations which define the velocity and position, you can approach all these questions. So let us continue with like some maximum time. T maximum will be equal to 2 multiply t prime. So if it takes certain time for this body to reach point 1, it will take the same time to reach point 2, which will be the last moment of this finish of this projectile motion. So it will be twice t prime, and it will be v like 2 multiply v naught sinus theta divided by g. So this is the maximum time of duration of the flight. Okay, let's go to another slide. And let's say we want to figure out what will be the distance. So there's this distance L, its maximum distance it will travel along axis X. So we remember that our coordinate X is equal to V naught cosinus theta t. This is constant. And now if we substitute here instead of t maximum, which is equal to 2 v naught sinus theta divided by g, we get the maximum length. It will be L equal to v naught cosinus theta multiply 2 v naught sinus theta, and this everything divided by g. So here we have v naught square multiply cosinus theta multiply sinus theta, and here is also 2, I forgot, and divided by g. So according to trigonometry rules, we can transform this 2 multiply sinus theta multiply cos sine theta as so it will be equal v naught square multiply sinus of 2 theta divided by g. Yeah, so this is equation for maximum length. And you can see if you analyze a bit this equation, you can see what maximum value of sinus is unity. And it changes from 0 to unity. So it will be equal to unity when 2 theta is equal to 90 degrees, because sinus of 90 degrees, or pi divided by 2 radians, will be equal, this 2 theta will be equal to pi divided by 2 radians. It means that theta should be equal to 45 degrees. So maximum length will be reached at the theta equal 45 degrees. Oops, sorry, not percent. Okay.
Mr. Bruce, can I ask a question?
Yes, sure.
What value for G we should use in our problems? Like we can use 10, we can use 9.8 or 9.81.
Yeah, usually it's 9.8, but again, depends how precisely other parameters are defined in the problem. Usually it's 9.8, but if other parameters are defined to the second point, like second number after the point, then use 9.81.
Thank you.
You're welcome. Okay, so also what else? Now we know the maximum length, so maximum time, the duration of the flight, maximum height, and maximum length. What I would like to underline, there is another option to deal with this projectile motion, which is kind of useful. So we can derive an equation which describes the trajectory of the body. So let's try to go for that. That's important thing, because it shows you another approach to deal with these equations. Plus, we can also determine one of these parameters using calculus. So a kind of interesting approach. Let's try to do that. So again, come back to our y and x components of motion, of projectile motion. So it will be v naught multiply cosinus theta t. Then y is equal to v naught sinus theta t minus jt square, the gt square divided by 2. Okay, so what can we do now? In order to get the equation for trajectory of this body, we need to get rid of time. So we did something similar before, but let's do this specifically for this case of projectile motion. So we define time as a function of x. So it was different before because we defined time as a function of velocity and then substitute for the position. And that was a relationship between our position and this change in position and change in velocity. But here we will
get Professor Bruce. Can you show the previous slide?
Yes, sure. Yeah, here.
What does theta equals 45 degrees means?
Theta equal 45 degree means that this L distance which the object travels
Yes.
will be maximum for given velocity. V0.
Okay. Will be maximum for V0, right?
Yeah,
Yes.
for
Okay,
we
thank you.
have fixed velocity, then we need to throw our object at the angle of 45 degrees, theta equal 45 degrees to get maximum length along the axis X.
Sorry,
Okay, thank
L
you.
is like the distance from in x-axis or the
Yeah,
whole x-axis?
L is distance in X axis,
All right.
0 to the position where body lands, and H is distance along the Y axis, which is the height of our trajectory. So this is the highest point of our trajectory. Okay. Good. If you don't follow something or don't understand, interrupt me, we can come back to that. You need to be able to follow what I'm talking to you, and since it's kind of very limited interaction nowadays, would be really nice if you don't understand something, just stop me and ask. Okay, thank you for questions. Now we have we want to define t as from this equation. So let's do it. It will be t equal to x divided by v naught cosinus theta. Okay, now since we already defined this time, we can substitute it here in equation for y. Let's do this. So y equal to v naught sinus theta multiply. So instead of this t, we put its value like this equation, x divided by v naught cosinus theta. Then we have minus g, and here it's t squared. So it will be x squared divided by 2 v naught square cosinus square theta. Okay, you see that this is t squared. Okay, so let's see what we get out of it. So here v naught and v naught, they cancel it out. So ratio sinus theta divided by cosinus theta, it is tangents of theta, but leave it like this because later we will need to come back again to this ratio. So it's more convenient just to leave it like this. So let's write x multiply sinus theta divided by cosinus theta, and then minus g x squared divided by 2 v naught square cosinus square theta. Okay, now we have this equation, and this is the equation of parabola. We have first and second order of x. So we have a function y as a function of x, which gives us the equation for the trajectory of our projectile motion. Okay, so now let us again ask this question: what will be the maximum height of this what is the maximum height this body will reach while we have these initial conditions, this projectile motion with given conditions. We know that our trajectory looks like this. And so this is x, this is y. So this is the equation which describes this trajectory. And here is the maximum of this function, y versus x. So according to calculus, derivative of this function y over x should be equal to 0 for the maximum of the function. Here we have x maximum. So this derivative at x maximum is equal to 0. Why? Because at maximum we don't have any movement, neither up nor down. So we don't have change in y. And derivative is like dy over dx. And if dy is 0, then derivative is also 0. So this is the condition which comes from the calculus and helps us to define the maximum of a function. So we have this function, it's y versus x, and let's take first derivative of this function. So what will be y prime will be equal. So here we have x, this is sinus theta, cosine theta are constants. So then we get sine theta divided by cosine theta. And then we have minus, so we have x2 here. Here will be 2gx divided by 2 v naught square cosine square theta. Okay, so these 2 and these 2 we can cancel out. And our condition for the maximum is that this derivative of our function is equal to 0. So when it will be equal to 0? It will be equal to 0 when this part will be equal to this part, so they cancel each other. And that's why we can write the following. Will be sinus theta divided by cosinus theta equal to gx divided by v naught square cosine square theta. From here, we can write the expression for x. X is equal to v naught square multiply cosine square theta multiply sinus theta and divided by cosine, like g cosine theta. Okay, I guess we didn't miss anything. So now we have to cancel out this square and cosine theta in the denominator. And we get the expression for, so also keep in mind that this is a product, cosine theta multiply sine theta. So it can be changed by sine square theta divided by 2. Yes. Yeah, because then it should be 2 sine theta multiply cosine theta. It's equal to sine square theta. And here we don't have 2, so we need to divide it. It will be v naught square multiply sine, sinus of 2 of squared theta. It's so too much of things are going here on this slide. We probably need to go to another slide. So let's copy this equation and go to another slide. So we got x equal to v naught square multiplied sinus theta multiplied cosinus theta. And now this can be written as v naught square multiplied sinus square theta divided by, here I forgot g, divided by 2g. And we see that this is, if we compare it to our previously derived equation, this is L.
Excuse me, Professor.
Yes.
Isn't it sine 2 theta, not sine square theta?
No. It should be.
Because sine 2 theta is equal to 2 multiplied to sine theta cosine theta.
Yeah, let's double check. No. So we get condition when for x when our function reaches maximum value. So let's have again here. So we have x and y. This is our trajectory, and here we have maximum, which reaches at height h, and here is x maximum. So this is our x maximum, means the position along axis x at which our trajectory, our function reaches maximum value. And this is the L. So this is total length of the travel along axis x will be L, and this maximum position is L divided by 2.
But Professor, sorry. But in previously we write the formula of L like v squared sine 2 theta divided by g.
That is true, but let's come back to this equation. So v squared sine 2 theta. Yeah, you are right. I missed that part. Yeah, 2 theta, good. Divided by 2. Yeah, everything is correct. Now, thank you for correction. Then we have v squared multiplied sine 2 theta divided by g, this equation for L, and now we have just divided by 2. So it's L divided by 2. And this is the way how we can define the position of this maximum h, and substituting this value now in our equation y as a function of x, we can get also the maximum value h at x equal to L divided by 2. Yeah, you can repeat this, check this by yourself. So we will not spend too much time on this. But yeah, so this is the way how you can approach this problem with the equation which describes the trajectory of the projectile motion. So not necessarily that you always need to work with time. You can skip time, get the y versus x function, and also analyze this equation. So it depends on conditions what you get for your problem. It can be more beneficial to have this approach while solving certain problems. Okay, and of course, yeah, don't forget, don't mess square with 2. That is important. So thank you for following up. Okay, so now I think with this question, we are more or less done. If you have any questions later, we can come back to this, but let us go further and consider one interesting case of more complex motion. So let us maybe consider a case of rolling wheel. So we have some wheel which is on the ground and it spins on the, like, rolls over the ground with some velocity v naught. And since it spins with, so its one-dimensional velocity is v naught, then linear velocity of this point on the wheel is also v naught in absolute value. So let's say maybe in order to distinguish, we don't call it v naught because it's different vector, it's in different direction, but in absolute values, v is equal to v naught. And this is because v is equal to omega r, which is like radius of this wheel. And this technically equals also to v naught, the motion along the one dimension, like which is, let's say, some x axis. So what is our question? We would like to know how this point on the wheel, what is the velocity with respect to ground? So like, let's consider ground as an immobile system of coordinate. We have these wheels rolling on the ground and we need to add 2 velocities, so v naught and v at given time. So let's maybe draw another figure here, a bit larger, and try to figure out how to answer this question. So let's say this is our radius, this is angle, let's call it some angle phi. Here is our point on the wheel. And let's consider a system of coordinates which goes like this. So y and x. So we have this vector v naught, and also we have a vector v. So this vector v, which is linear motion of uniform circular, this is linear velocity of uniform circular motion, we can consider its 2 components. It will be vx, and here we have vy. And of course, for the direction of x, we need to add this v naught because it's along the axis x. Here we add v naught, and all these can be considered as vectors. And that's why the total velocity with respect to ground will be our let's call it, yeah, I don't know, let's call it V prime. That's one which we want to figure out. So in order to answer this question, let us see the projection, like have the projection of our linear velocity to axis x and y. So keep in mind that linear velocity is always perpendicular to the radius. So this is our radius of the wheel. And here we have right angle. So if we have angle between the vertical line V here, then here between the velocity, a linear velocity and axis x, it will be also angle T. That's why we can write that Vx is equal to V naught multiply cosinus phi, and Vy is equal to V naught multiply sinus phi. Then we keep in mind that along axis x, we have two components, Vx plus V naught. So that's why our total velocity along the axis x component will be V naught multiply cosinus phi plus V naught. This is our V naught, the motion of the wheel along axis x. And this is equal V naught 1 plus cosinus phi. So, and the total velocity, which is V prime now, will be equal, like absolute value, will be equal to square root of the V naught 1 plus cosinus phi here square plus y component. This is x component, and then we need to add y component, which is V naught square multiply sinus phi square. Okay, so this is our absolute value. And now let us open the parentheses here in the under the square root. So we have V naught square plus V naught. Or actually, we can get rid of V naught already from the square root, because we have V naught here and V naught here square. So we put it outside the square root, and we have here 1 plus 2 cosinus phi plus cosinus square phi, which is we open this parenthesis here, and plus sinus square phi. So what is seen here, these guys, cosinus square phi plus sinus square phi is equal to unity. Okay, so here's the question, what is V prime? So V prime is the total velocity of point, this considered point on the wheel with respect to ground. So here we have ground. So we have linear velocity of the point because of uniform rotation, and also another velocity which is along the axis x because of rotation of the wheel itself. So it happens in one dimension, along the one dimension. Okay, so this is equal to unity, and that's why we have v naught square root of 1 plus so 1 plus 1, then it will be 2. So we have already can write 2 plus 2 cosine phi. Yes, and then we have v naught. Let's delete this guy here. Square root of 2 multiply 1 plus cosinus phi. And let's keep this in mind. So we go to another slide. We don't have space here. So v prime is equal to v naught square root of 2 multiply 1 minus 1 minus or plus. Forgot already, plus. Okay, 1 plus cosinus phi. And we need to keep in mind that 1 plus cosinus phi divided by 2 is equal to cosinus square phi divided by 2. So this you can check in the geometry, and that's why we can substitute this parenthesis by 2 multiply cosinus square phi divided by 2 equal to v naught square root of will be 2 multiply 2 cosinus square phi divided by 2. So now we get rid of 1, 2 and this square because we have square root. It will be equal to 2 v naught multiply cosinus phi divided by 2. And this is the answer of this particular question. Let us consider this before we finish. We're almost done here. So we have this wheel and point here with angle phi. So it moves with respect to ground. And we are looking for this v prime, the absolute value, with respect to ground. So if this phi is equal to 0, cosinus of 0 gets its maximum value and is equal to unity. And this is this case when this point on the wheel is on the top, its linear velocity is added to velocity of the spinning wheel. So we add these two velocities and it will be v prime equal to 2 v naught. And when this phi is equal to 180 degrees or pi, so phi over 2 will be equal to pi divided by 2. So cosine of pi divided by 2 equal to 0, and that's why v prime is equal to 0. So what happens here? In this point, when it touches the ground, a linear velocity will be directed in opposite direction to the velocity of the rolling wheel. So this is V naught. And these two vectors will cancel each out. And it makes sense because when wheel is spinning on the ground, this point where wheel touches to the ground is always fixed to the ground. So the velocity is equal to 0. If we have this condition that we don't have sliding between, if you don't push acceleration on your car so much that wheel starts to slide while keeps in the same position, doesn't move forward with respect to the ground. So if it's not the case, this point of the wheel which touches the ground will always have 0 velocity with respect to the ground. And this is like two most interesting cases while analyzing this equation for resultant velocity of a point on the wheel which rotates on the ground. I believe that these two examples of projectile motion and more complex motion of rolling wheel will help you to understand better motion in two-dimensional space, and definitely should be helpful for you to solve certain types of typical problems. Thank you very much for attention, and hope to see you again on Friday. If you have any questions on this two-dimensional motion, you are welcome to ask them. And I believe that on Friday it's time to start the laws of motion. That will be our main topic for our discussion on Friday. Okay. Thank you very much for attention. Have a good evening.
Thank you. Goodbye.
Bye.
Bye.
Goodbye.
Bye, guys.